Welcome back to the ENE 310 exam preparation videos. So we have covered treaty section, the first 4 study units, and now we are going to look at Schoolman's section from study unit 5 till study unit 10. Those will be the next series of videos that we are going to cover. And the videos will be presented in the same way. So we'll be going over the theory and then we will be going into some examples. So with study unit 5 is basically just amplifiers. And everybody who's watching this video has passed ELI. So therefore this is not the first time that they see an amplifier. So you know how it works, and we did briefly touch on amplifiers in the first 4 study units. So the video for this study unit, the theory part, won't be explaining too much on the theory because everything that you need to analyze your amplifier and to design your amplifiers is given in the notes that you are given in the exam. So we are gonna first of all start with our Sallen-Key, right? So this is your Sallen-Key low pass filter here, and these are your standard equations. When you're using your Sallen-Key, you rarely use your standard equations. So for your Sallen-Key low pass amplifier, you can design for it in 3 ways. You've got your equal components, your unity gain, and the modification, which is independent of gain. So you can choose any of these 3 ways to design your amplifier, but there is a little bit of a note that I made here. There should have been unity gain. So for your unity gain amplifier, your unity gain amplifier is dependent on your value for N, which is here. Why is it not drawing a square? Well, that was an epic fail. So it is dependent on that formula, that value for N, which is greater than or equal to 4q squared. So a nice way when you're designing your amplifier is that you choose your N to be a factor of 10. So your N could be 10, 100, 1,000. Well, 1,000 is actually pretty big because the highest Q value you can achieve with these amplifiers is about 10. So choose your value of N to be a factor of 10 because your N has an effect on which capacitors you're going to use. So if your capacitors value differ by a value of 10, it is much easier to get standard components for them instead of having an N, for example, like 8.54 or some random number. So that is a little tip about when you're designing unity gain. And then after that, you've got your Sallen-Key high pass filter, and there really isn't any shortcut to designing this like we had in our low pass filter. So here, excuse me. So here are your design equations. here you are going to have to rough it out, but you rarely design high pass filters in ENE 310. Most of the time you are going to be designing either a notch filter or a low pass filter. This is because with your high pass filter, there's a bit more work that's involved in it. As you can see here, there's no simplification of these design equations. You literally just need to bit bang it until you get something that's right. So that's your high pass filter. There's not much to it. Then you've got your band pass filter, and these are your simplified design equations for your band pass filter for your Sallen-Key. And as I said, with these amplifiers, there's really not much explaining because all of this is in your notes and you do have access to all of these things during the exam. And then you've got your Sallen-Key notch filter, and there are your design equations. Excuse me. So maybe, okay, let me just draw your notch filter. Okay, that was a little bit extreme. No filter will do that. So your notch filter has an output like that. Your board plot of your notch filter will look like that. And excuse me. And there's really not much to teach here because, as I said, you've seen all of these different types of amplifiers in your semester tests and in your practicals and in ELI. And so Sallen-Key isn't the only amplifier configuration that you can use. There's also multiple feedback, and there is also state variable and biquad and a whole other bunch that other people have made up. So for your multiple feedback, this is your multiple feedback bandpass filter, and these are your design equations. But if you have this bandpass has one condition that is not explicitly stated. Your gain must be greater than 2q squared. But if you want a gain that is smaller than 2q squared, you use these equations. So this R1A and R1B is basically taking this resistor. Let me get some white out here. So you're replacing this resistor with that's R1B, R1A. So that is these two values here, and by using this voltage division here at your input, you can decrease the gain of your circuit. And then there is your multiple feedback low pass filter. So for here, as we said, there's not really much teaching. Here you design equations, and one approach for your multiple feedback low pass filter is described here. So in this approach, it's similar to the unity gain of your Sallen-Key. So you choose C1 and C2 to have a ratio of n, which is greater than or equal to 4q squared multiplied by 1 plus the gain that you would like. And then you design for R3 using this equation. Your R1 is R3 over gain, and your R2 is that. So that is one way to work out your values of your resistors for your multiple feedback low pass filter. And then after your multiple feedback low pass filter, there is the notch filter. And it says design a band pass filter with negative output like the MFB beta F. Design a summation amplifier. So for your notch filter, it is a little bit more complex for your multiple feedback. As you can see, as I said, these are the notes that are going to be available to you. And for your notch filter, you basically have a band pass filter here and a summing filter there. A summing amplifier, my bad. And that is how you create your band pass frequency response using multiple feedback. I'm not really going to analyze this because there is a lot of working to prove how this is a band pass filter, but this is your band pass filter for multiple feedback. So in your multiple choice questions, you may have seen something that looks similar to this, where they block out the bandpass filter and simply write a block that says bandpass filter, and then you've got your summing amplifier there. And then they ask you what topology this is. So now you know why this topology is a notch filter. Because as we said, your notch filter for multiple feedback is your bandpass filter with a summation amplifier. So the next time you see that multiple choice question, you won't even need to think about it because now you know it's going to be a notch filter. So if you want to have more control over your amplifier, you are going to more likely use more amps, and one sort of configuration that uses more than one amplifier is your state variable filter. So your state variable filter is shown right here. And the nice thing about this filter, I think it's absolutely epic. I have the utmost respect for the person who had designed this. So you have a high pass output, a band pass output, and a low pass output. So by designing this one filter, you have access to all three parts of the filter. So if you sample there, you're going to see a high pass. Oh no, that's a low pass actually. You're going to see a high pass. If you sample here, you're going to see your band pass. And if you sample here, you're going to see a low pass. Now that is absolutely incredible, and big ups to whoever designed this. So the way you design your state variable filter, as stated again, is just your design equations. And yeah, there's really not much to teach. I just thought that this is a very epic filter because you can have 3 different outputs. So a way to simplify your design is to use these equations. So basically you make your R's, R5, R4, and R3 equal, and R6 and R7 are equal to another value of R. And you make your capacitors equal, and this makes your calculating omega much easier. And then you can calculate your Q point using your ratio of R2 to R1, and then your gain of your high pass is -1, your gain of your low pass is -1, and your gain of your band pass is Q. So by using the simplified version, you are sacrificing control over your gain. So it's a trade-off of what's really important. In the previous slides, we covered the different topologies that we can use to create an amplifier. So in the previous slides, the amplifiers that we made, and we didn't actually do any examples, so we didn't make any amplifiers. So the amplifier topologies that we analyzed were all second order. They were second order poles, right? So if you would like to get a frequency response that has more than 2 poles, then you would have to cascade amplifiers together. So the approach for this is that there's actually 2 approaches to designing a cascaded amplifier. You can either design the whole thing yourself from beginning to end and cascade the amplifiers together, but there are certain things that you have to keep in mind, like having a dominant pole, making sure that all the poles are at least 1 magnitude away from each other, and the last thing would be your stabilization, because you are going to be designing an amplifier that has more than 2 poles, so therefore there is a chance that your amplifier may be unstable, right? And that is the one way where you can design your cascaded amplifier. The other way is to design it using a table. So this table is used when you would like to design a cascaded amplifier. All of the amplifiers here, well, these aren't amplifiers, these are just numbers. So the way that all of these have been calculated are such that you are going to have a stable amplifier. So that means your gain margin will be positive and your phase margin will be positive, compared to when you design the amplifier yourself, where you can get into trouble with your gain and your phase margin. Alright, so there's Chebychev, there's Butterworth, there's ellipse, and elliptical, and there's Bessel, 4 types. So there are 4 different types of amplifiers. You've got your Chebychev amplifier, you've got a Butterworth, you've got a Cauer, and you have a Bessel, right? So whenever you are designing an amplifier, chances are that you are going to be making a Butterworth amplifier. So your Butterworth amplifier looks really, really nice because it has... Okay, that's getting annoying. So your Butterworth amplifier it's smooth in the pass band, which is here, and it has a gradual cutoff of 20 dB per decade. Your Bessel looks like your Butterworth, but it has a lower cutoff than your Butterworth. So your Bessel is very relaxed, like just strolling around doing its job. So though that's for your Bessel and your Butterworth, but if you want to have a sharper cutoff, you have to use a Chebychev amplifier. So the one trade-off when you use a Chebychev amplifier is there are ripples in your pass band. So the amount of ripple that you want can be chosen by choosing the right table. That didn't make sense. So let me try that again. So your Chebychev has ripples in your pass band, and you can control how much ripple you want in your pass band by either choosing to design from this table or from that table. And there's also another table for 3 dB, but yeah, that's another story. So the one thing with your Chebychev is that if you have more ripple, that means it's going to cut off faster. As you can see, if you look at these two values right there, right? These are both second order low pass amplifiers. But you can see that the attenuation here, the attenuation is basically how low your amplifier, your attenuation is basically how much your frequency is being attenuated, because the whole use of an amplifier is you want to focus on these frequencies there, right? And all the other frequencies should be attenuated. You don't want to have them seeping into your main frequency. So to know how fast your amplifier is attenuating, you're going to be looking at this column, right? So that's how you decide. So this is how your Butterworth looks. This is the Bessel, and this is the Chebychev. For your Cauer filter, you've got ripples in both your pass band and your stop band. I should actually... So let me start by actually explaining what I mean by pass band and stop band. So your pass band is basically all of the frequencies that won't be attenuated, which are those frequencies, and your stop band is everything else on that side. So that I'm going to be using pass band and stop band a lot, so I just wanted to make sure that you know what I mean. You may not have encountered those terms before, but that's what your pass band and your stop band is. So for your Cauer filter, we said that there are ripples in your pass band and there are ripples in your stop band. And that's basically how your Cauer filter looks like. So back to our Chebychev filter. We can control how much ripple is in the passband by choosing to either design using that table or using this table. But there is something that I would like you to note. This is the okay, that was dark. That is the attenuation at 2 FC of your Chebychev. So if you want a 0.1 dB, you can see that the attenuation is less than a 1 dB ripple. So the more ripple you have, the faster your op amp will cut off. And so when designing your Chebychev amplifier, you need to consider two things. How much ripple are you willing to consider in your passband, and how steep you want the cutoff to be of your amplifier. And those things are shown in these two tables, where if you want a faster cutoff, you have to sacrifice by having a bigger ripple. And that's just one of the trade-offs of engineering. You can't have the best of both worlds. You can't have your chocolate cake and still look like a supermodel. So let's get back to where we were. So, as we saw in the table, the table doesn't have any frequencies. So I just copied a section of the low pass filter for your Butterworth, this table right here, just to explain this concept here. So for you to change from these values to your frequency, you take your f of o, the value here in the table, and you multiply it by your frequency, right? And Butterworth is really, really nice with this, because your frequency is always the frequency that you're designing for is the same frequency that you want, right? Let's compare that to your Chebychev, right? For example, here, let's look at there, right? Let's say you want to create a second order Chebychev 0.1 dB ripple at a cutoff of 100 kilohertz, right? So you would say F is equal to FO of the table multiplied by your FC, which is your 100 kilohertz. So here we see that this is 1.820. So therefore, you are going to be designing for 182 kilo ohm cutoff, but when you simulate this amplifier, it's going to have its cutoff at 100 kilohertz. This is just how your amplifiers work when you're using the table. You design for this frequency, but your output is going to be that frequency, where we said this was the 100 kilohertz that we wanted to design for, right? And that's basically it on this part. And so you choose your order of your amplifier. Let me just erase all of this. So in this column, what just happened? That column tells you the order of the amplifier, whether you want a first order, second order, third order, and such and such. And this column is the frequency of the table that you must multiply your cutoff with. As we said, if we wanted 100 kilohertz cutoff and we want a second order Bessel there, that means we would be designing for 127.4 kilohertz. Right. So that's how that works. Erase that. And then you have this column. That column gives you the Q factor that is desired to make the type of topology. You will notice that for your Butterworth, your Q factor is always less than 1. And for your Chebychev, your Q factor is usually greater than 1. So your Q factor is what makes that part. So if you have a higher Q factor, you're going to have a higher ripple. And that's it. The table repeats. So if you want your second order, you only need 2 parts. But if you want, let's say, a 9th order, for example, which is pretty extreme. So your first stage is defined by those 2. Your second stage, those 2. Third, fourth, and 5th stage. And you just do the same procedure. You design each stage, and you can choose whether you want which topology you want to use, whether you want to use Sallen-Key, multiple feedback, state variable, or biquad filter. So this table basically tells you your Q value and the F value, the frequency value that you're gonna be designing for. And that's pretty much that table. And if you want to make a high pass filter, instead of multiplying here, you do that. You have your cutoff frequency over your F of table. And that's how you design for your high pass filter. Nothing else changes. You follow the same steps and you're going to get your high pass filter. So I see here that I've made a little note here that says that when making a filter that has an odd number, 1, 3, 5, 7, 9, you should design your second order stages to have unity gain, and then place the gain stage in your first order filter. The reason for this, it comes back down to stability and your gain bandwidth product. The next part of study unit 5 is taking a look at jigs. The way jigs are used is that you may use them to simulate a inductor or a resistor using, you can simulate an inductor, or you can simulate a bigger capacitor by using a small value for your capacitance. That sentence may have not made sense, but let me try to explain it to you. So the way your jack is connected is by this node A. So that's how it's connected, where this is just one part of the circuit and that's another part of the circuit. So the circuit sees an impedance here that is equal to Z1, Z3, Z5 over Z2 multiplied by Z4. So if you were to replace, let's say, any of the top ones in Z1, Z3, or Z5 with a capacitor, what your circuit would now see is Z1, Z5, Z2, Z4. So basically what your circuit sees is this capacitance being multiplied by this factor. So therefore you can use a very small capacitor and it can be seen by the circuit as a large capacitor. And if you want to simulate an inductor, you would replace either Z2 or Z4. And the replacement I used was 1 over SC, because that's your impedance of your capacitor. So I replaced Z3 with 1 over SC to get to this point, to show you that your circuit sees this capacitance being multiplied by Z1 by your circuit sees this capacitance here being multiplied by that. So therefore you can simulate a large capacitance using a small capacitance. You can also simulate an inductor by replacing by replacing either Z2 or Z4 with a capacitor, and then that's how you will simulate your inductor. The one thing that you must always keep in mind is the way that the circuit sees your jack. Your circuit will always see your jack in terms of ground. So that is how your circuit sees this jack amplifier. So therefore, if you were, for example, asked to simulate this inductor here, as you can see, this inductor is not being grounded. So therefore, you cannot use a jack to simulate this inductor. All the components that you simulate have to be earthed. Come on, man. So the one other thing that I didn't mention that you can synthesize in your jack is a frequency dependent negative resistance, as seen here. So to get a frequency dependent negative resistor, you substitute a capacitor, 2 caps here. You substitute them into Z1 or Z3 or Z5, and that ends up happening. That's your frequency dependent negative resistor. This will come back when we are designing the direct design, the passive op amps. Passive op amps. No, your passive filters. So, in your direct synthesis approach, you are making a RLC ladder that you will use as your amplifier. The reason why you would do this is because amplifiers consume power, and if you have a power sensitive application, you might want to use passive what's the word? You may want a passive amplifier instead of an active amplifier, because your passive amplifier will not consume power from the source. So, with your direct synthesis approach, I think this is much better explained by doing an example. So for now, just know that you can create a passive network using your direct synthesis approach. There is also a table for this. If you want to create a Chebychev passive amplifier, there's a table for it, and it is also found in your notes. And basically, it's not much different from the table that we looked at previously. So, I put two notes here. So this is I won't say this is an example. This is more of an illustration of how you will use your jigs in your direct design. So you would have designed this amplifier to have a certain cutoff at a certain frequency, and then you see that you've got an inductance there, and all of those, right? So, because those inductances are not in reference to ground, we cannot replace them with a jig. So to try to breathe. So the procedure would be to transform your capacitors and your inductors. And that transformation is done here. As I said, this will be explained better in an example. So you transform your capacitors and your inductors to look like this. So now, because your inductors are in reference to ground, you can replace your inductors with a jig network. And that is how jigs are, that's the application of jigs. You use them to replace those bothersome inductors that always appear.